Okay, so in the previous lecture, we used the Van Kampen theorem to find fundamental groups of some examples like the sphere, the torus of N genus, and also, that's pretty much it. And we also found the fundamental group of a two-petal rose. And so yeah, we discovered that this is a very powerful tool in further differentiating topological spaces from each other. Especially, femtopological spaces. We use this to differentiate sort of definitively, but not really fully say that two spaces are different from each other. So it's a form of categorization. And we used it to show that a sphere is fundamentally different, completely not homomorphic to a torus, say, or with itself, but with a hole inside it. I have a sphere, but I punched a hole in it. It's not the same as this over here. So Van Kampen tells us, this here. It's not the same. And so it's our way of or our first way or method of determining whether two F spaces are precisely the same or completely different. And so, okay, we're going to reinforce that by discussing or making some more structures out of a new space constructed out of the real numbers and the fundamental space of all possible femboys. So, in femboy theory, we discuss a bijection between the naturals. We discussed a bijection between the naturals and our fundamental femboy space F, mathcal F. So there was a bijection from this here, and then that implies, of course, the existence of an inverse that takes F and then takes its elements onto the naturals. And that bijection is that for every femboy listed F sub I indexed by a set J, we take it to the corresponding natural number I. And one reason why it is a bijection is that if we assume that it is a surjection, if it's a surjection, that implies that we are mapping more than one element onto one element in the domain. So the pre-image of the image under this map is more. So the cardinality of the pre-image exceeds the cardinality of the image. So it would assume that we have some Fi and Fj that gets mapped onto a single element I. But that cannot be the case because I over here are the same, but J over here is I. And the morphism or the original mapping is an equivalence class between this and this. So we're saying this femboy is precisely the ith femboy. So if we're saying that Fi is equal to I, we're also saying here in this case that F is also equal, Fj is also equal to I. But because it's an equivalence relation, it holds that this would, transmit or it's transitive. So we would say, or we would assume this time that Fi is equal to Fj. But we established that these two are distinct elements because we list them as two different letters, I and J. So it must be that these two are not the same, but because of this, they should be the same. So we have ourselves a contradiction. So the only way to resolve this is by saying that because these two are mapped onto the same thing via an equivalence relation, these two must be precisely the same, and that I is just J, or J is just I. And so it's really just one element being mapped onto another element. So there is our bijection. I didn't use that as a proof in femboy theory, but here's a more comprehensive, explanation of the proof or justification for why it's a bijection. Okay, so we created a bijection between the naturals and our fundamental femboy space, and then we also carried on over the notion of successors and addition, of course. So we also had to carry on the structure in order for it to be a true bijection. It must hold that the rules in one set also hold in this set or the structure. Okay, so how about the integers? Well, actually, this will all be discussed, or this is all discussed in foundations. Constructing everything from the natural. So it's all a matter of making a plane, a natural plane, and then sort of corresponding every line that passes through, or points along a line that passes through a natural number on the axis or on the plane with an integer. Okay, so equivalence class of a pair along the plane itself, so you can call them roots or zeros, and then sort of correspond those equivalence classes with an integer. Okay, so so we're going to be applying the Van Kampen theorem to find the fundamental groups of some more implied structures. So these implied structures will come from a different space that is neither any number system that we know right now, nor the fundamental femboy space. But it is a combination of both of them. So really, this would have that we require a bijection between them. So okay, so this set is what we call the real femboy space. And we denote it via math BBF, math BBR, n. It's an n-dimensional space. It could be one-dimensional, which is just a line. It could be two-dimensional, which is a plane. It could be three-dimensional, which is three-dimensional axes. It could be a four-dimensional space, n-dimensional space. It always generalizes to n. So what is this space? So this space, so I'll make a definition. So definition. The real dash femboy space is denoted F R n. So it's an n real femboy space is the set of n tuples which is f1 fn such that each fi for I is greater than 1 equal to 1 but less than n is corresponded with a real number I. I know it's counterintuitive to use I here because I is usually used as the imaginary unit, but we're using it as an index here. So it's corresponded with a real number I. And the same proof holds as to why it's a bijection, because again, if we assume that we're mapping multiple tuples of f, or multiple pairs or tuples and tuples of femboys onto a single real number, it would assume, because we're using essentially an equivalence relation, that's an equal sign, that would mean it's, it's transitive. It would require that all of these distinct femboys, all of these femboys in this tuple, which we claim to be distinct, would actually be the same, because they all are equivalent to that single real number. So it can't be that, because we define them to be distinct. Okay, so let's revise our definition a bit. So it's a set of distinct n tuples. So it could be a pair, which would give us a two-dimensional space. It could be a triplet, which would give us a three-dimensional space. A quadruplet, which would give us a four-dimensional space. Now, order here sort of matters, of course, just like how swapping x and y would give something that we didn't quite want, or that's not quite the same as if we didn't swap them. So that's FRN. And we can now revise our definition of various femboy structures, such as, FSN, FBN, FTN, what else? What other femboy structures? FD2. Open and closed, by the way. Assume I'm implying both open and closed ones. Now we can think of these guys as subsets of FRN. Now you may be thinking, how the heck is this a subset of FRN if the domain over which the pairs that construct these things range over just F? Well, we just simply replace. For each of these guys, for every femboy that we use to construct these guys, every tuplet of femboys we use to construct in the atlas, we change it. So we say that it's an element of Fn, right? We just change it to instead saying that the tuplet F1 Fn is an element of FRN. That's it. And then we've essentially carried on over the notion or the idea of it just being part of the fundamental space or n fundamental space, and then just saying that it is now a subset of it. So there. So one way of thinking about the femboy structures we have constructed thus far, especially in femboy theory. So the crucial relation for a set of femboy tuples or a space of femboys, for it to be a subset of FRN, or for it to be FRN, is that these guys have a bijection with the real numbers. So that means the fundamental femboy space that we use to construct FRN must have the same cardinality as R. And there would exist positions of femboys that are considered, not natural numbers. Like, for example, the 1/2 femboy, the pi femboy, and the eth femboy, the square root of 2, the square root of the second femboy, stuff like that. All that matters is that these guys have a notion of being less than another thing, such as how e is less than pi, and the square root of 2 is less than 2e, and 1/2 is less than all of these guys, or 1/2 is less than all of these except square root of 2. So there is still a notion of ordering, because the real numbers is still ordered, although not really countable. Okay. So it doesn't quite matter if our space is countable. All that matters is that our space, our femboy space, has the same cardinality as R. Okay. So free yourself of the notion of place, and now think of them as individual numbers, or think of each of these guys as being represented by a non-natural or non-integer number. It could be an integer, it could be natural number, of course, but we want to generalize as much as possible in order for us to actually make the bijection. Okay. Now, because FRN has a bijection with, because FRN has F and then R, and it implies a bijection between F and R, it must also hold that relations from R and F carry on over to FR. So we now say that FRN is a ring with respect to the maps plus the digs FR cross FRN, or just FR, and takes two inputs, cross FR takes to FR, so it's closed, and this multiplication operation FR cross FR, two inputs, one output, like how multiplication is. So it's a ring with respect to those maps. And the operation, so addition of two femboys F1 and Fi and Fj, I and j distinct, is precisely Fi plus Fj, which is equal to the F sub I plus j femboy. And it follows from the usual notion of adding real numbers I and j, which gives us I plus j, which is just I plus j. And then the multiplication of this is that this, and then Fj is equal to Fi times Fj, which gives us the F sub I times j femboy. And then it carried on over from our notion of Ij taken to I times j, and that would be j times I, because this is R would form an abelian group under this, and it would form a monoid under this operation. That's what constitutes or qualifies it as a ring. And so because we're carrying on over notions from R onto this structure, then of course it becomes a ring as well. So FRN implies these two operations over here. Okay, so now we've discussed this, let's move on over to the actual structures. Now, I actually wanted to make this video the other day, but it didn't quite register, so now I have this lecture, and good thing is that this lecture is more structured. Okay, so let's make the structures. What are the implied structures, or more implied structures we get from this space? Of course, we have the other structures. We already have Fs1 or Fsn, Fbn, Ftn, Fd2. Also, we have the femboy annulus. We could construct one from the complex numbers, but we're only working with the real numbers right now. So there's an additional structure, which is a complex femboy circle, which is consisting of relations or all real numbers that are it's in the complex plane basically, but we will discuss it in a different lecture in femboy theory. So the first structure implied structure we have for this is the thigh, of course. Very important object. We've discussed this at the very start, but we failed to rigorously define what exactly a thigh is. So we're going to do that here. Definition. An end thigh is the structure T to the N, which is equivalent by definition to a gluing between two end spheres. And alpha is inside but not the entirety of one of these end spheres. And the end sphere is homeomorphic to a, hold on a second. Okay, so S to the N is homeomorphic to n-dimensional analog. Okay. Analog of the surface of revolution generated by the function y equals minus a cosine h, or the hyperbolic cosine phi times x plus alpha plus alpha. So this, where this a, phi, x, alpha, and a, sorry, that's not alpha, that's a, small a, all exist. So these exist, all of these exist in FR. FR 1, 2, 3, 4, 5. A, phi, x, alpha, and small a exist in a 5-dimensional real family space. Oh, sorry, not M, it's 5. FR5. So what we're just saying is that we're taking these 5 distinct elements from FR. So we're picking 5 elements from FR, and then we're putting it to this function to get the shape that we want, and then we rotate it about a principal axis to get a surface of revolution, and we claim that the S sub n, or S to the n, which we glue together, or glue copies of, two copies of together, is precisely homeomorphic to. So the real thighs are constructed from this long thing, which is an n-dimensional analog of the surface of revolution generated by the function, which is a cosine h function. And the justification of why it's a cosine h function is that, okay, there are many ways for us to construct these things or describe a thigh, or mathematically or abstractly define a thigh in terms of a graph or a bijection. We can define it as an exponential function, or we could a power of x, perhaps, like x squared. This could very well look like a thigh. It could be a Gaussian function, just e to the minus x squared. And then, yeah, or a portion of a cosine function. So down, up, down. So cosine. Cosine of x. Okay. So the thing is, what we're concerned about is that, yeah, okay, these guys look very much like thighs, but the problem is they don't quite look like it at the end. When we approach the origin, we notice that it becomes very sharp, it becomes somewhat sharp, And although it looks a bit cushy, this one here looks too soft. This one here is roughly like this. So we don't want this, but when we do examine the graph of a hyperbolic cosine function, it looks like this. And look at that. It's a perfect model of a thigh in our abstract mathematical plane. All of these are FR2, by the way. Okay? So yeah, this is what we chose to be our standard way of generating the solid of revolution, which becomes our, which is a basis for the n-dimensional analog, which we glue together to form the n-thigh. Okay, so one thing that you guys need to note is that this is just a shell of it, okay? And one thing I want to state is that it was a bit wrong for me to have shaded a top portion of the thigh to indicate, you know, thigh highs, because that would indicate that it's a filled region or an area, whereas an actual thigh right now doesn't have an area. It's just a ring of points, not really ring, but a string of points or a collection of points that so happen to form a thigh. There's nothing in here, nothing inside here, there's nothing inside here, there's nothing inside here right now. And that is why we're going to define the next structure. And that is the meets. What is a meet? So a meet, an n meet, okay, so for a one thigh is just a flat one. Two thigh would be a three-dimensional thigh, a surface, and then the three thigh would be a four-dimensional femboy thigh, and then on and on until n dimensions. And we will, later in the course, we will be using the Hopf vibration to embed the four thigh into the three thigh. Okay, later in this course. Okay, so the n meets. Definition. The n meets. There are two versions of a meet. There is an open and a closed meet. So right now we're going to talk about the open meet. The open n meets is the structure which is m to the n, which is equal by definition to a gluing of two open balls Bn glued to itself such that alpha is inside the open, but not the entirety. Okay, so it's the open meet, and then we say that B to the n is homeomorphic to the n-dimensional analog of this time, instead of surface of revolution, we're thinking about the volume generated by the surface of revolution. So it's the n-dimensional analog of the volume generated by revolving the relation y is less than minus a cosine h of phi x plus minus alpha plus a by a principal axis. This is precisely why I said that it's a bit wrong to shade the upper portion of a thigh, because that would indicate it's a ball now, or a disc, instead of a sphere or a shell. So basically, it's not really a shell, because a shell is a generalization of an annulus. Okay, there, by principal axis. So if it's the n equals 1 case, it's just a one ball, a flat sphere or a flat circle that's filled in, or the surface area or the area generated or area bounded by a circle. Okay. And the same relation holds here, is that A, phi, X, alpha, and A are inside FR5. Or just FR basically. All of these come from FR. And the reason why we chose greater than, this is greater than a prescribed Y, is that this generates an area or a region of space rather than a string of lines, or a collection of points, I mean, not lines. When equals generates a bijection, now we're thinking about an injection for this over here, because we're taking a bunch of points in some Y and then we're mapping it onto some few points inside a circle. Alright? So this gives us a filled-in thigh, a shaded thigh. If a while ago our cosine H function gives us something like, oh no, sorry, that's ugly. Give us something like this. This would be Y equals dot dot dot. You know. This one over here would be shaded. So this is why we call it a meat. Because it's the inside of it. It's the meat of the thigh. It's the muscles, the tissue, so on and so forth. It's the meat. Now this is for the one-dimensional case. Well, topologically speaking, geometrically speaking, it's 2 dimensions. For the 3-dimensional space, it's just this as well. But then it's now a volume. Yeah, instead of an area, it's a volume now, a volume element. Yeah, it's a volume. So it's now revolved around. Because we revolve the area around the principal axis, we sweep a volume. Yeah. Like, if I rotate this around the principal axis, we end up sweeping the volume of a cylinder. So that's it's open end meat. Now the closed end meat is simple. This time there is a boundary. So the closed end meat, we just replace this by the boundary of the closed ball. Because there's a boundary now, we want to glue them about their surface, which is the boundary. So this time alpha now, which we used to, the notion of sticking 2 subsets together, taking similar subsets from both of these and then gluing along the line, so we're essentially doing a surgery, becomes to have been taken from, turns out to have been taken from a boundary. So there. Oh, one more thing. Equal. So it could be equal to now. So there's a boundary. Actually, a while ago, this here would imply that this is just shaded, or this in here is broken lines. To indicate that there is no boundary, because it looks like there was a boundary. So there. That was for that. For a closed thigh, of course, those lines are filled in and are solid lines, not broken lines. That's why, and then yeah. So that's a closed end meat. Now you may be thinking, okay, how about a disc? What is our femboy version of a disc? What if we glue 2 discs together? We get something which we call the prosciutto. And a prosciutto is a French, I believe, originally a French dish. A French dish composed with a very thinly sliced piece of meat. It could be ham, it could be beef, I think. But the general idea is that it is a flat piece of meat. So that's our ticket, or that's what we will define or talk about next. So the definition. So like the ball, the prosciutto will be closed and open, or so there are 2 versions of it. The closed prosciutto. The closed prosciutto is the structure math calc P equal to the gluing of two closed disks along a boundary or a subset of the boundary alpha. So D2 glue D2 along an subset alpha such that the subset alpha is a subset but not the entirety of the boundary D2. And of course D2, we have defined what exactly a meat is now, and you guys know that a disk is basically just, the interior of a circle plus the circle. Now that's a closed disk at least. An open disk is a circle or a closed disk without boundary basically. So this is a disk, since it's closed, we say that this is homeomorphic now to the one meat, closed one meat. And we'll define this later, but I'll say it now that this closed one meat is the interior at least. So the closed one meat without boundary is the interior of the one thigh. So yeah, instead of me having to write out that entire thing again with the relation, we'll just say that it is homeomorphic to the closed one meat. So that's our closed prosciutto. So it's a two-dimensional figure. It would look like this. That's our closed prosciutto. Now, an open prosciutto is this, but we break the line, or break the boundary. Or the line that acts as the boundary of the object. So it's now a broken line, and then this becomes the open prosciutto. So it's now the closed M1 without boundary, or the open one meat. Okay, that's the open one meat. So that's the open prosciutto. Okay, so far so good. What are the relations between the prosciutto, the meat, and the thigh? What exactly are the relations between these things? Well, you guys already know that one dimension is like the flat one, okay? So we'll consider the flat case. So the one thigh is actually homeomorphic, or it could be precisely the boundary of the closed one meat. The closed one meat. And the closed one meat is homeomorphic, or the boundary of the closed one meat is homeomorphic to the boundary of the closed prosciutto. The closed prosciutto. The interior of the one thigh is equal to the open one meat, which is homeomorphic to the open prosciutto. These are practically the same. So this is the important relations that hold between these guys. So the one meat is the inside of the one thigh, and we can generalize this to n, n shapes. So the n thigh, or the interior of the n thigh, is the open n meat. The n thigh is precisely the boundary of the closed n meat, and the prosciutto has nothing to do with these two because the prosciutto is only a two-dimensional object. So here, when we generalize it, we sort of lose sight of the prosciutto because it's inherently just a two-dimensional object. Okay, so now that we've made these structures, let's go ahead and distinguish them, or let's prove that these guys are actually the same or equivalent to a circle or to a ball. Now, for this lecture, I know I discussed this, or I know I mentioned these structures, but we will only be focusing on the thigh and the boundary, of course, of
of the meat and the closed meat and the closed prosciutto. And the reason why we're doing that and not considering the solid ones, because topology doesn't care about whether an object is filled or not. What it cares about is if it has holes on the object or, you know, not. That's what we want to determine, right? If these things are precisely the same or not, by constructing or computing their fundamental groups using Van Kampen. Or basically just corresponding them with a circle. If they are homeomorphic to a circle, then basically they would have the same fundamental group. But we kind of don't have a computation yet for the fundamental group of a ball. I know you guys can probably correct me on that. Just say it in the comments below if there is a fundamental group for the ball. But when I searched, there's really none. It's mostly just the sphere or hollow shapes, or hollow manifolds or hollow topological spaces. So let's do this thing. So let's consider the one thigh. Or the two thigh. It could be two thigh, but let's just consider the one thigh for now. Okay, theorem. Theorem. Okay. The fundamental group of the one thigh, independent of a base point, is isomorphic to the fundamental group of a one sphere, which is precisely the integers z, or the free group generated by one generator. There. So that's our theorem, our first theorem. So theorem 1. So theorem 1 of this lecture, not theorem 1 of the entire course. So proof. You notice now that this is a gluing of this and itself. So I have an S1 here, I have a circle, and then I have another circle. And then I take away a subset alpha from both of them. So I'm going to indicate it here. I take away a subset alpha from both of these guys. And I glue along the missing parts so as to create a link and thus fill in the void. That's what it means, or that's the definition of gluing, according to surgery theory, or geometric topology. And you notice now that there really is no holes left. This over here is a closed convex subset. We just need to bulge it out, and this is just homeomorphic to a circle. And likewise, if we consider the fundamental groups of these guys, we have this over here. So essentially we're adding the fundamental groups of these two spaces when we connect them together. So F1 of this S1 union 1 of this S1. And because these two are essentially the same shapes, the underlying set of these fundamental groups, those curves that we construct out of, that we embed into these, or homotopy equivalences that we put into these to show if they're the same or not. By the definition of a set, if we combine a set's elements with, a copy of the elements, so take the unit of a set and itself, we would just get that set. And likewise, with an operation, if we take the unit of an operation, it's not really defined, so it's best to just say that we get the exact same operation. So doing that here would just give us a group that's just homeomorphic to itself, or isomorphic to just the fundamental group of S1. So that's part required proof over here. So T1 is by definition the gluing between S1 and itself. It's denoted by this hashtag, of course. I failed to mention that. So we're already implying that we take away alpha and then stuff like that. That's already implied. Now, S1 glued to S1 is still homeomorphic to S1. Okay? So this implies that the fundamental groups of both of these guys are combined so as to be union. And that would be isomorphic to the fundamental group of just the one sphere only. And the one sphere the fundamental group of this here is essentially the fundamental group of the combination of both of these. S1, glue S1, which is isomorphic, sorry, not really equal, isomorphic, and then it's isomorphic to 1 of S1 union 1 of S1. Oops. Okay. So far so good. Okay, now because we said here that this is equal to this over here, that this is isomorphic to this, then this over here is isomorphic to just that, the fundamental group of S1, which is just the integers, which is free group over 1 generator A. So by way of transitiveness of these isomorphisms, the fundamental group of the one thigh is precisely Z. QED, quarter demonstration, or Halmos to demonstrate the end of the proof. So this picture over here is needed for us to show really that all of this is true. Okay. Next theorem, we're gonna generalize now to n. So t to the n for n greater than 1, because we're only now we're just considering the case of 1, but the case of greater than, dimension 1, if you have a surface, it has a trivial group of 0. Okay. So now let's consider the 2 thigh or the n thigh. The fundamental group of the n thigh is isomorphic to the fundamental group of the boundary of the closed and meet. It's isomorphic to the fundamental group of the boundary of the closed prosciutto. It's just isomorphic to the fundamental group of the Sn sphere for n greater than 2 or greater than or equal to 2, which is just 0, the trivial fundamental group. Okay, so the proof of this works just like the proof of theorem 1. So again, this is theorem 2. The proof of theorem 2 works the same way as the proof of theorem 1. So we basically show that because Tn and is a combination of or gluing of two n spheres that are homomorphic to something that looks like a thigh, we essentially show that the fundamental groups are combined and stuff like that. Okay, so that's what we want to do. That's what we want to do for the proof. So proof. So by definition, Tn is equal by definition to the gluing between two n spheres. And we will actually employ Van Kampen to this point, because for n greater than 2, we would require a different proof wherein we have to split the space into 3 different subsets that are all path connected, and because they're path connected, we can apply Van Kampen. Now, these spaces are all path connected, absolutely path connected. Pick 2 points inside them, connect them, still inside the set, so it's path connected really. So we really can apply Van Kampen on these guys. And because I defined them to be gluing between 2 sets that are path connected, we can essentially still apply Van Kampen on this, suppose if we really want to. But yeah, mostly all the work of Van Kampen is involved in proving that this over here has a fundamental group of 0, which we already did. All right, so we don't need to do that here anymore. We just need to apply the previous theorem or the proof of the previous theorem and carry on over to the general case. Okay, so I have an n sphere, but we'll visualize it as a 2 sphere. And then I have another 2 sphere. And then I take away a subset of it. Which is alpha, and then I glue along these guys here. So this becomes like that. This carries on over. And then this becomes just something homeomorphic to a regular n sphere, which we visualize to be a 2 sphere right now. And then, you know, same operation here. One of an Sn union one of an Sn is isomorphic to just one of Sn. Okay, so using this picture over here, we're going to use the logic of the previous one to show that it's 0. Okay, so 1 of Tn is equal, this implies this, by the way. So the homeomorphicness of the nthi to a gluing of these two implies a homomorphism, which could be an isomorphism between their fundamental groups. So that's a fundamental, or very important fact that we need on our belts in order to even show that the fundamental groups are like that. That they are induced homomorphisms. Okay, so that is equal to the fundamental group of a gluing Sn by the definition of a nthi, and then we break that up as a union, because the operation of this is just that over here. Okay. Union 1 of Sn, and yeah, because the fundamental group of Sn independent of a base point is 0, that tells us that 1 of Sn union, oh actually sorry, that's actually just, we're using this fact over here, this picture that is isomorphic to just 1 of Sn. Now 1 of the pi 1 of Sn is equal to 0. So this is just 0 union 0, which is homomorphic to 0. So that, yeah. Oh, wait, sorry. No, I'll write the full string. So the pi 1 of Sn is 0, so the pi 1, because the pi 1 of the nthi is precisely 1 of Sn, which is precisely 0. And that ends the proof. So we've essentially shown that not only these three are homeomorphic to each other, as we dictated from the identity a while ago that I mentioned, and we proved it, or we proved that identity through the course of a theorem and through computing the fundamental groups. So this is the reason why it's so important. Now, for Sn having a fundamental group of 0, just use Van Kampen to prove that. And it's a very trivial stuff. It just involves taking subsets from the identification space and then modding out a normal subgroup from the free product of two spaces that are, and all of those are path connected. It has to be. We discussed in the previous lecture. So yeah, this is it. Really cool stuff. And actually, that's it for this lecture. I know it's a bit short. It's not as like 1 hour as it might have been, but this is our application, some deeper application of it at least. And they could just be this. Just remove Yeah, I guess.
No, it goes all the way, right? I erased that. I don't know why I erased that.
There. Yeah, that looks cleaner. Definitely looks cleaner. And then that's just homomorphic to this. We just bulge that out and return to. There's no holes there's no holes, so it's really like that. And there really are no holes in these things. There are no breaks in the line, so they're really the same. So there. So geometrically speaking, no breaks in the graph in the line. Algebraically speaking, or topologically speaking, there is a homomorphism between these two. We can just bulge them out. And algebraic topologically speaking, or algebraically topologically speaking, they all have the same fundamental group. So we have a strong basis. Now, another powerful tool that we can use to prove equivalences or differentiate these guys is through homology, which will come later in the course. So yeah, that's it for this lecture. I know we're a bit early, 4 minutes early, but yeah, consider that as like a bonus time, I guess. So yeah, that's it for this lecture, and that's a good place to stop.